Like to give my warm welcome to Amity Uttarwal, and I just want to. I think this is what I found really interesting in her bio is that in her free time, she writes and commits code to the Bitcoin core as the only identified female developer. So let's welcome her with a warm applause.
Hello. Hi. Thank you for coming. My name is Amity, as mentioned, and I work at Coinbase on the crypto operations team. And I'm excited to talk to you today about why cryptography matters and look at a few of the technical fundamentals of the cryptography that we have used through history and are using today and are building systems on. So the word cryptography comes from the ancient Greek words crypto and graphene, which mean hidden or secret and writing, respectively. Today, the word cryptography is defined in the Oxford Dictionary as the art of writing or solving codes. At its core, the concept is simple. It's any time that you're trying to keep information concealed. I remember being a little girl and passing notes with my friend across the desk, and we would come up with these elaborate methods of keeping it secret so the boys across the table wouldn't know what we were talking about. And that's pretty common, right? It's pretty common for kids to come up with some sort of mechanism to keep things secret, either from real people or a lot of times imaginary people. So cryptography fundamentally is something that's fairly natural to us. So what we're going to talk about today is, I assume, no prior knowledge. So we will cover the basics of what is cryptography and some of the language that you might have heard already, but just define it. And then we'll take a quick look at some examples of mechanical ciphers in history. And the two main concepts that we will be covering are symmetric and asymmetric encryption techniques. And we'll relate that to how it's used on the internet and how this is used in Bitcoin. So cryptography is ancient. The first identified use of it was in 1900 BCE, which is almost 4,000 years ago. And it's seen everywhere from Mesopotamian clay tablets to within Egyptian hieroglyphs. It's been around for a really long time, and it's deeply woven into human history. And it's become more relevant today because this is a depiction of that game of telephone that you're probably familiar with as a child's game. And the idea being that the first person is trying to pass a message through many other people and get it to this last person in the chain. In the internet age, when you're trying to buy something from a store owner halfway around the world or send a message to a family member in another state, it's close to impossible to create a direct connection with them. And so you have to send messages through many other people. So it's really important. How do you keep those messages intact? How do you make sure that only the people you want to read the messages are the ones that are able to read it? And how do you make sure that the message you send doesn't get maliciously messed with or accidentally even? So let's cover a little bit of the lingo. You start with a plain text message, such as hello, and you encrypt it to be a ciphertext, such as URYYB. And that would be the message that you send and is hopefully hard to decode or understand what your original message is. And in order to return to that original message, you would use a decryption algorithm. And so this whole thing is called a cipher. The pair of algorithms used to encrypt and decrypt a message is known as a cipher. And that's how you get your ciphertext. So one of the earliest and simplest examples of a cipher is the Caesar cipher, which is a form of substitution cipher. A substitution cipher is when you take a message and you systematically replace the letters of that message with other letters. And a Caesar cipher is one where the way that you replace those letters is by offsetting it within the alphabet. So here what's depicted is that you would go -3, so D turns into A, and etc. Apparently, back in the day, Caesar actually always used 3, which doesn't seem like a very secure mechanism, but that's what I read. Another example of a Caesar cipher is the ROT13 encryption, which is short for rotated by 13. And that's what I use to encrypt the word hello into the ciphertext URYYB. And so this shows you the scheme, and it's slightly interesting because you can use the same method to encrypt and decrypt. Like, so with URYYB, if you were to encrypt that again, that gives you back hello because of the fact that the alphabet's 26 letters and you're shifting it by 13. So in this example, the cipher being used is a Caesar cipher, and the key is 13. So if you had this message and you wanted to return to what the original message is, those would be the 2 pieces of information that you would need in order to get hello. Another type of cipher is a transposition cipher, the most simple example of which is turning the word hello into ole. A transposition cipher is when you just rearrange you use the same letters, but you rearrange them in some way that makes it harder to understand. And so a more complex example is this columnar transposition cipher. And we'll just walk through an example. If I wanted to encode defend the east wall of the castle, then I could create a grid, and on top I would make an arbitrary key, and then I would put the words into the grid. And then I would rearrange it so that my key was in ascending order. And then that would give me the text that is my encrypted text. So from this ciphertext on the bottom, what somebody would need to know is that the cipher being used was a columnar transposition cipher, and the key was 42531, which would both give them how many columns there are, as well as how to rearrange these letters so that you can get the original message. One of the most advanced mechanical ciphers that has been used in history is the Enigma machine, which was used heavily in World War II. It was actually really, really impactful because the Axis powers were in favor in the war, and when the Allies were able to crack this cipher, they were able to turn the tide and gain power. So it's kind of wild to take a moment and think about how these encryption technologies have deeply influenced the history of our human society and what might have been different had things gone differently. But we'll talk about how the Enigma machine works. At its heart, it's a substitution cipher, so each letter gets replaced through a systematic method with other letters. And it kind of looks like this typewriter over here. But it's got several layers of obscurity that made it very difficult to crack and decipher. So one of them is that there are these multiple wheels. So there are multiple layers of substitution ciphers, and they would rotate every time that you input a message. So the string AAA would not map to something like GGG. It might map to something like XIW. And so the way that the Germans were able to communicate with each other is that they had these really large code books that they just kept at their stations. And so they would set up the Enigma machine every day with a different starting key. And they just had these books that kept their daily keys in them. And so that's what it was. One of the things that helped with the cracking of this code was a flaw that you can't ever map, because of the way the circuitry worked, you can't ever map a letter to itself. And so that was a fundamental little key that helped in cracking it. And then also repeated phrases, like the word Hitler was used a lot, and that was a giveaway in helping crack it. So then came computers, and everything changed. One element is it helps you with the decryption because it helps you compute more possibilities or brute force things. But the much more profound implications of computers is that now there's a lot more possibilities for the message that you've encrypted. Originally, like, language was the main method for having your ciphertext, and like the possibilities were contained to language, maybe some digits, maybe some characters. But with computers, the key size could be quite small, but the number of possibilities became exponentially larger. And just to give you an idea, this like 256-bit is, you know, very common, not that big, but 2 to the 256 possibilities is that number is comparable to the number of atoms in the universe. So if you want to brute force that, it might take you some time. So everything we've been talking about so far is our forms of symmetric encryption. And what that means is that you use the same key to both encrypt and decrypt your text. So like for your cipher, that same key works both ways. And that's great. But in the internet age, when you're communicating with different parties on insecure channel, aka the internet, how do you make sure that you both have the same key? Definitely code books would be a very different world if every time you typed in your bank account, you had to like look up a code book, and then you went to your next website and you had to flip the page and type in a different code. That might not work that great. So this was actually a fundamentally difficult problem to solve, and only in 1976 was a huge innovation introduced by Waltman Diffie and Martin Hellman. And they won a Turing Award for this innovation and this work, and it's really fundamental, and we use it all of the time. But it's the concept they introduced is a way for two parties to agree on a shared secret using only an insecure channel to communicate. So the way we're going to talk about how this works, and it fundamentally relies on an idea of one-way functions. Mathematically, like, what that is saying is it's really easy to apply the function in one direction, and it's really, really hard to do the opposite. So we're going to walk through the Diffie-Hellman key exchange using this example of paint. The one-way function that we're using is saying that if you've mixed two colors of paint together, it's really hard to reverse that and actually separate them into different colors. So we have Alice and Bob who are trying to create a shared secret. And in the middle here, that represents the insecure channel where people, spies, friends, everyone can listen. And so we start with a common paint color that everyone can know. In this case, is murky yellow. And Alice and Bob come up with their secrets. These are ephemeral secrets, but it's important that they don't reveal what those are. And so they mix it with the common paint color, and they get this mixture. And then they can send each other that mixture. And because of this fundamental assumption that it's hard to extract from that, that's okay for it to be public information. And then what they do is they apply their same secret color again. And because the ordering doesn't matter, they both come up with this shared common secret, which is what they use moving forward in order to encrypt the rest of their communication. I mean, obviously not with paint, but in the math of it. So the Diffie-Hellman key exchange relies on a one-way function known as the discrete logarithmic problem. And we won't go into this too much, but just at a high level, like this is the function, b to the k mod p equals a. And just a reminder, what mod is, you might be more familiar with the percent terminology, but it's just the remainder. So 5 mod 3 is 2. And what the discrete logarithmic problem is saying is that if you have b, k, and p, it's easy to compute what a is. But if you have b, p, and a, it's computationally very difficult to compute what k is. So in this example, it wouldn't be that hard because the numbers we're using are really small. But if we remember how big that keys can be based on that previous slide, when you get sufficiently large with these numbers, it's so computationally expensive for this to be derived that it's practically impossible. So in this case, k is 8, if you're wondering. So we're going to apply that to the paint image, and I know this slide can be a lot, but the idea is pretty similar. Like we have Alice and SpongeBob. Funny play on Alice and Bob. Thank you, practicalnetworking.net. But we have these two numbers that are public information and agreed upon, and then Alice and Bob both create a ephemeral private secret, and they just apply the discrete log problem using like these numbers that they've agreed upon and their secret, and then they share that information with each other, and then they apply that problem again, and they come up with a shared secret that they can use to encrypt their messages moving forward. So in practice, we use end-to-end encryption using a lot of text messenger apps. The application which has the strongest privacy guarantees is Signal, which you might have heard of. And they came up with a whole protocol for privacy that includes end-to-end encryption, but a lot more different aspects of it. So and what they do is they store your keys only on your device. So it's not in the cloud. It's not like the company doesn't have your keys. If you add your Signal account to a new device, you actually won't be able to see the history of your chat because that new device doesn't have the shared secret in order to decrypt the messages. So you'll create for that session a new shared secret, and that's what like your safety number has changed is a message that they show you. So WhatsApp also has pretty strong privacy guarantees as they follow the Signal protocol. There are some other messengers like Facebook Messenger, Google Allo, and Skype all have opt-in encryption, but it's not enabled by default. And iMessaging has end-to-end encryption, but you trust Apple with your key management. So Apple would have the ability to decrypt your messages, but someone lurking on the network doesn't. But surprisingly, text messages has no encryption, so it's actually fairly easy to lurk and read those. So in review, symmetric encryption is the idea that two parties use the same key to encrypt and decrypt their messages. It's important to be able to establish a shared secret via insecure channels for the internet to work well. And so Diffie-Hellman key exchange is used and different variations of that. And the way it works is it relies on a one-way function known as the discrete log problem, which given this formula, says that calculating k is hard even if everything else is known. And so this is kind of important. Like the discrete log problem is a fundamental assumption, and if this were to be cracked, like if someone were able to calculate k based on those other things, a lot of the guarantees and like a lot of the things that we kind of take for granted in our communication would fundamentally change. So it's probably not going to happen, but just good to know what the assumptions are. So another form of encryption is called asymmetric encryption, and that's an idea where you use a different key to encrypt versus decrypt your messages. And so the most common form of this is called public key cryptography. And while these are conceptually different, these terms are actually used fairly interchangeably. Because public key cryptography is so prevalent. And the way public key cryptography works is that there are these key pairs, private and public key. And your private key is something that you keep secret. You keep it only to yourself. But your public key is something that you might distribute to the world. And this, the metaphor I like to use is for, it's like your house address. You might give your address to your friends, your bank, your favorite junk mail providers, but only you hold the key that allows you to open up your mailbox or enter your house. So yeah, it's kind of like a digital version of that. One thing that's really important is to know in order for this to work is that it's easy to get from your private key to your public key, but it's really hard to get from your public key back to your private key. And that's what fundamentally makes it work. So there's two main use cases of how this is like a really useful feature and in digital systems. The first one is to send a message. Say we have Alice and Bob here, and Alice wants to send a message that only Bob should be able to read. So she can use his public key to encrypt the message, and then using his private key, he will be able to decrypt the message. So you can send a message to an intended user. And the second use case is kind of doing the reverse. It's an ability to prove who you are. So if Alice encrypts a message using her private key, that message can be decrypted using her public key. And then you know that, that private key must have been Alice, and so I know who she is, or, she is who she says she is. So this is called a digital signature. In practice, we use this a lot for internet and browser communication. Every time you visit an HTTPS website, you're using transport layer security. And this actually builds on both the public-private key cryptography as well as using the Diffie-Hellman key exchange to encrypt a communication. So the way it works is you type in an address, and the certificate authority will return you a canonical public key. And so you visit this website that is known provider of something, and then once that connection is established, you create a shared secret, and you use that shared secret in order to encrypt the rest of your messages. So let's just take a moment and think about how different our world would be without these technologies of encryption in place. Can you imagine all of the information that you give to apps? What if you were just revealing that to the world? Like every time you were to access your bank or reveal your location to Google Maps or send your credit card information to buy something online, or even just the emails. This isn't something that we want to be public information. If you want it to be public, that should be a choice that you're making, not something that you don't realize is happening. And so having these encryption schemes have fundamentally impacted our ability to use the internet. Digital commerce probably wouldn't be a thing if we didn't have these technologies in place, and so many other aspects of our life. So the impact in our society is quite profound. So now we'll chat about how cryptography works in Bitcoin. Something that's really interesting is that it's actually not encrypted. All of the information is there and can be verified by anyone, but it does use cryptography. And the two main things that it uses are digital signatures and cryptographic hashes. So we'll talk more about that. But yeah, it's a little bit surprising because everyone thinks cryptography and blockchains and like it must be this wild encryption scheme. But there are some like newer chains that have been coming out that rely more heavily on encryption and trying to obscure like how much was sent and via what form and things like that. But the main ones, Bitcoin and Ethereum, don't actually use any encryption. So in Bitcoin, your wallet is actually pretty much an abstraction of your private key. And that's what gives you identity. Like that is what is your ability to keep funds. And so you distribute your public key to your friends or anyone you want to send you money, but you keep your private key as your way to be able to spend those funds. So if Alice wants to send Bob some Bitcoin, then the way it works is first she would prove that she is who she says she is by using her private key to create a digital signature, and that shows the network that she is the one who is able to spend these funds. And then she would create a transaction that transfers the funds into Bob's wallet. And what that means is she associates that with his public key. And she says only the owner of the corresponding private key to this public key is allowed to move these funds in the future. And so that's kind of how the cycle works. Then he can prove who he is by using his private key as his digital signature and sending that to another public key. So the one-way function that is used to go from a private key to a public key in Bitcoin is known as ECDSA, which is short for Elliptic Curve Digital Signature Algorithm. And I'm not going to go into it today. This could be like a whole nother talk of its own. But it's really interesting, and if you think so too, then I encourage you to look it up or talk to me after. And so the second mechanism that we were talking about that's fundamental to why Bitcoin works or how it works are cryptographic hashes. And these are pretty cool. An example of a hash is I take the word hello and I put the SHA-256 hash, which is just a specific algorithm. This is the one that's used in Bitcoin. And I get this kind of random looking thing on the other side. There are a few different properties of hashes that make them so functional. And one of them is that they're deterministic. Even though they're random, you will always get, if you SHA-256 hash the word hello, you will always get this same exact output. Another one is that the size is consistent. You can take 300 bits of information and put it through a hash function, and you can get 256 bits on the other side. But this is also true if this information that you start out with is 3 million bits of information. You will still get 256 bits. So in Bitcoin, a network where you're asking as many individuals to run software as possible, the more people who run the software, the more secure and trusted the network can be. So it's really important that you have small enough messages that can be sent around and everyone can receive it. And so having hash functions to be able to take large amounts of data and send them to one another and compare them and things like that is fundamentally important to making the network work. Another really important property of hash functions are that if you change anything, the output totally changes. So on the right here, or I guess your left, we have 0000, and this is the resulting output. Whoops. But if we just change one bit, which is the smallest piece of information that you can change in computing, then the resulting hash is totally different. And this is important because in Bitcoin, this is how you compare that you and I are talking about the same history of what happened, and we agree to that. Because if you changed even one small piece, whether maliciously or accidentally, of anything in the history of what happened, then our outputs would be totally different looking. So with very little information and very quickly, we can say, yes, we are talking about the same history. So yeah, hashes have a lot more properties, but the fact that they are cryptographically secure is really important. And what that means is that the only way you can predict what the outcome of the hash is going to be is by running it on the information and exactly that information. If you could predict what that outcome was going to be, it's kind of like breaking that one-way function idea, and the security of Bitcoin relies on the fact that you can't predict that. And so if you're interested in this, the term to look up and learn more about is proof of work, which you might have heard of, because this is fundamentally how Bitcoin is secured. So to review, Bitcoin is not encrypted, but it does rely heavily on cryptography via the form of hashes and digital signatures. So the ability for different nodes, which is just computers running software, to agree on what happened and validate that they are on the same page and not change history, as well as to identify that only people who are supposed to spend funds are actually able to spend those funds. And so to wrap up, this talk is called Why Cryptography Matters. And I think that it is fundamentally important. It's been around for a really long time in human history. And while before the internet age, it was the most common uses of cryptography were in like warfare and politics and these sorts of things. Now that we have the internet, we're using it all of the time because when you go online, you only want to be talking to who you think you're talking to. If you were just revealing all of your information to everyone, that would be extremely problematic for many obvious reasons. And so we just touched today on, one or two ideas of how encryption techniques and cryptography are used in our day-to-day, but there are many, many more, and they're fundamentally important to how we work as a society. And as we're building these future systems, they are these cryptographic techniques are becoming embedded deeper into mechanisms that we might be using on a daily basis. And what I would like to leave you with is why I think Bitcoin matters. Bitcoin and blockchains are a fundamentally radical technology because they are introducing a totally new trust model. In human history, we've only really had two trust models. One is direct, and you build trust with an individual by getting to know them directly, but that quickly hits capacity. Dunbar's number is about 150, and that's like this idea of how many individual relationships you can maintain. And so in order to scale to the size of society that we have today, what we've done is develop a hierarchical trust model. And that might be you trusting the certificate authority to route you to a true website, or putting trust in your bank that they will validate where your funds go, or in the website, the Airbnb, so that if the person providing you a home does something weird, you'll get a refund. We have tons of examples of whether it's your school or your workplace, the internet, everything of this hierarchical trust model. So what blockchains have come along and done is say, hey, using this math, using these computer techniques, we can come to an agreement of what happened without having to actually trust one another. And that's fundamentally radical shift in what that means for how our societies can scale. And so this technology is still pretty new. There's plenty of problems with it. But the way that it is able to create those guarantees are through these cryptographic mechanisms, through these mathematical models. And so I think it's important to learn a little bit about and pay attention to, hopefully contribute to. If anyone's interested in learning more about Bitcoin, please come talk to me. And that's all I've got today. Any questions?
Thank you, Amity. There's one question from there are two questions from the live audience, but I'm just going to pick one and maybe see if you can answer that. The question is, do you see any good use cases of symmetric cryptography algorithms, or have you come across them? And as far as my knowledge goes, that they're still being used now, but what do you think about them, and can you cite an example or give us a good use case?
Of symmetric encryption?
Yeah.
I mean, that was kind of what we can find it, but so TLS uses it, but like when the text message example, this is end-to-end encryption. You're creating a shared secret using symmetric encryption, and so that using that shared secret, you both encrypt and decrypt the messages. So that would be my example.
Cool. Thanks.
Yeah.
Are you going to share the slides? Sorry. Are you going to share the slides?
I would be happy to. I don't know. I'll have to. Does anyone know if the slides get shared?
Yeah.
Oh, yeah. I can post them on Twitter.
Yeah.
Totally.
We can work with her to get the slides, and we can share them as a resource.
Okay. Yeah. So I'll do it through Women Who Code, but also you can. Oh boy. All right. I'm Amizi on Twitter, and I will post my slides.
Okay. Awesome.
Hi. My question is, so you were saying that with Bitcoin, there's no encryption. Mm-hmm. So is there something that they're using, or they're creating something for encryption for transfer of, you're saying basically transferring any kind of information as far as Bitcoin, no encryption at all?
No, so there's no encryption. The way that some privacy works is that you don't know it's hard to associate a person or a user with the public key that you're getting. There's a lot of mechanisms so that from one private key, you can generate all sorts of public key addresses. And so when you send funds, it's not like you're always sending to the same exact address. But it's like if you have the state of the network, you can figure out that this account has this many funds, or, I mean, it's not really an account-based model, but you can create this ledger of how much is where. And so it's all public in that way. But in order to make the jump from, yes, this like string of numbers and letters is Amity, and Amity has this much money, like that's close to impossible.
Hello, this is Flory, and I have a question about cryptocurrency. I know that, like Bitcoin, it provides anonymity and transparency in transaction. But why there are so many kinds of different cryptocurrency in the market, and what's the real value for them added to the digital currency market?
All right, so there are a few things in there. Bitcoin provides transparency. I would not say it provides full anonymity because of that transparency. Some things are able to be like tracked and reversed, and there's some advanced mechanisms in order to be able to analyze the data of the chain. Okay, and then your question is, why are there so many different currencies? I think that there's a lot of answers to that. There are a lot of different projects that are trying new things. As I mentioned, one of the things is more advanced like encryption mechanisms. So there's these things called like zero knowledge proofs and snarks and starks and all sorts of stuff. And so people are trying to fit different use cases or believe that the technologies, so maybe having less transparency to have stronger privacy guarantees are some of what the projects are. Other people, there is a lot of projects that you might have heard of that build on Ethereum. And Ethereum is the underlying chain, but there's a lot of like tokens that work on top of Ethereum because it has the ability to hold state. And those are a lot of projects that are looking for more of like application fits. It's questionable how long many of them will live. But there's, we talked about like hashing, and hashing is the fundamental idea that's below proof of work. But there's another consensus mechanism that's being iterated with in many projects called proof of stake. So fundamentally, it's a pretty new thing. So there's a lot of projects that are trying to find the solution that makes the most sense, because there are many, many issues. Like there are scaling challenges, privacy challenges, like the list goes on and on. But there's also a lot of excitement and people who are like, yeah, my project, it's great. So I think the reason there are so many is for a variety of reasons. Any more questions? Yeah?
Thank you. You mentioned that public key cryptography is almost synonymous with asymmetric key cryptography. Is there an example you can give of something that is asymmetric key but not public key?
No, I can't. I was looking at that, but conceptually, there could be different schemes for having like encryption and decryption keys being different. But everything I was able to find, like even the Wikipedia page is just like, asymmetric cryptography, public key cryptography is. So I don't have any examples of existing schemes. I think that would rely on having a mathematical model that would work that way. But maybe one day.
Thank you.
I think in the interest of time, we can take one more question, if there are any more questions in the room. Okay, no. Great.
Cool.
Thank you, everyone. Thanks for joining us. If you have any questions about cryptography, you know who to reach out to. Yeah. If you have any questions about our online blockchain community track, feel free to come and chat with me. I'm here around for the entire day. if you want to know how to join the community, how can you contribute as a volunteer, as a speaker, or whatever you're looking for in blockchain, I'm here to help you guys out. Have a great day.
Thank you.
One sec.
Yeah, one sec.